Okay, so finish up hopefully with polynomial functions, finding all rational zeros. Now, there is a theorem, and it's kind of like the last shall go first kind of thing, is kind of how I remember it. But say I have like 2x to the fourth minus 3x squared plus 8x minus 10. The way you can figure out where it might cross the x-axis pretty, we're talking fractions, rationals. So ratios are fractions or integers. Nice, 2, -2, whatever, a half, 3/4, -3/4. Is you take all the factors of the last, so plus or minus 1, plus or minus 10, what else? Plus or minus 2, plus or minus 5, okay? And you divide it by all the factors of the leading coefficient. This has to be in order from high power to low. Okay, so this is a constant. And then divided by plus or minus 1, plus or minus 2, because those are the factors of the first. So the last shall be first. All the factors of the last, all of the factors of the first. Now, if you divide these by 1, it's not going to change anything. And I'm going to put them in order. So plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. But if I divide by 2, notice like 1 divided by 2, I'm going to get fractions. So plus or minus a half. What else? 10 divided by 2 is a repeat. That's 5. 2 divided by 2 is a repeat. That's going to give you 1. 5 divided by 2 is no, though, or a new one, though. So these are all the possible rational zeros. So that means this is where, when it does the little loopies, this is where it could cross the x-axis. These are the things I want to check. Now, when I was in high school, I misunderstood this. This is the rational zero theorem. Only integers, only fractions. So for example, if you try all these and none of them work and you're like, well, it doesn't cross. Well, yeah, it could cross at, say, the square root of 2, the square root of 7, the square root of 13, right? Like these are not rational numbers, right? These are irrational, like pi. They go on forever, they never end, but they're still numbers, and the function can cross at these. So again, the only thing this gives you are the pretty ones, okay? Now, usually that's enough to get it down to something that you can factor or do the quadratic formula for to maybe get these guys, okay? So just know the rational zero theorem, the last, all the factors of last over the first. And again, if you have a different thing that helps you memorize it, go for it. But again, it only gives you pretty ones. It will not give you radicals, and it also will not give you imaginary numbers. All right, I'm going to pause a second and I'm going to bring up a problem so we can try it, see how it goes. Okay, so say you're asked to graph this polynomial function. You're like, ooh, odd power, right? And no negative to reflect it. So you know it's going to, do stuff like that for n behavior. But you don't know the zeros. You don't know that. And so you're like, oh, I'm going to factor. Factoring by grouping. Take out an x squared, you get x plus 7. But notice when you take out a 3, you don't get the same factor to get another thing you can pull out. So factoring by grouping does not work on this. So then you're like, okay, what do I do, right? And you don't want to sit here and sub in input and hope to get an output of 0 to say, hey, I found an x-intercept. So this is where synthetic division and the rational zero theorem comes to the rescue. The last, so plus or minus 1, plus or minus 3, you don't need the repeat, and plus or minus 9, 1 and 9, and 3 and 3. Those are the only factors of 9. The last over the first, which is 1. So that's not going to do anything. So what this is telling me, I need to check a positive 1, negative 1, positive, negative 3. I have 6 things that could work. Now, again, if this is radicals, that I don't know. All right, so I'm just going to try one of them. We will see if it works. All right, so I'm going to do synthetic division. So I have a 1, 7, no zeros needed, 9. Remember, you always bring your arrow down. All right, now, so I'm going to try, I don't know, I'll just try 1. Okay, 1 times 1 is 1. That's 8. That's 8. That's, what is that, 23. Yeah, that is not, that's not looking good, right? The fact that I have all these positives and I keep adding, so a positive 1 doesn't work. Okay, so maybe I want to try negative 1. So 1, 7, 15, 9. Let's try negative 1. Bring that down. Okay, negative. Add, I get 6. Negative 6. I get what? 9. Ooh, negative 9. This is good. Do you see how I know this is not a 0, but do you see how I know negative 1 is a 0? Okay, So on my list, I can say, ooh, yep, -1 is a 0. Now, you can keep doing synthetic division, hoping these other ones are going to be. Okay. But usually what you do is you get it down to something that's factorable, or you can use a quadratic formula. So we started out with x cubed. I did synthetic division once. So this is going to go x squared plus 6x plus 9. All right. I look at that. I'm like, ooh, that can factor. All right. So that would be x and x, 3 and 3. So there's my loopies. 3x, that, everything's positive. Now this guy, the factor, remember, is with the shift, the answer is a -1, but the factor is that. All right, so my factored form of this, factoring by grouping, did not help me. The rational zero theorem did, and synthetic division. So now I have my factors. I know that f of x equals x plus 1, x plus 3, and that is what, squared. So I'm not going to write it twice. Okay, how does that help me? Well, I knew earlier it was kind of that disco behavior, right? All right, where's it going to cross? -1, it's going to cross, and what, -3? 1, 2, 3. But at -3, it's going to touch, right? Because it's an even power. This one's going to go through. So I know my M behavior. I also know my Y-intercept. See that? If you sub in 0, it's 9. So I know that this is going to cross, you know, say up here at 9. Okay. So let's see, what do we say? Here it's going to touch, and here was to an odd power, it's going to go through. Okay. So this, I know actually it's going to go through there exactly. Now, I could sub in 2 to see how it behaves there if I care. All right. But otherwise, I might be like, oh, it's going to come up here. It's going to bounce, right? And then it comes right there. Okay. And, you know, close enough. Now, if you're like, well, Julie, I really want to know what happens at a -2. Well, let's sub it in. We have what, x plus 1 and x plus 3 squared. Okay, if I sub in a -2, that would be a -1 for that. -2 here would be what, 1. All right, so that's just going down to a -1. So, I mean, that's not that hard to, you know, I could get that perfect, you know, if I graphed it nice. Okay, so that's how that helps. Now, this is how you also find the square roots if you have radicals. You're going to get this, and it's not going to factor, and you're going to do the quadratic formula, and you're going to get radicals for that. So that's kind of how that plays out. All right, I'm going to pause. We'll do another problem. All right, the rational zero theorem says all the factors of 36, 1 and 36, 2 and 18, 3 and 12, 4 and 9, 6 and 6, plus or minus, divided by the factors of the first, which again, plus or minus 1 is not going to do anything. So these are all the things I have to check. Now, that's a lot. Okay. All right, I don't feel like doing that. Okay, so notice this is to the 5th power. What that means is there's for sure going to be 5 roots, solutions, answers. The thing is, or x-intercepts, the thing is some of them have multiplicity. So some of them might be duplicates. The other thing is some of them might be radicals, or some of them might be imaginary. All right, so this is kind of a, you know, high power, lots of things to check. So what I'm going to do is I'm going to graph it on Desmos to get a head start, okay? So sometimes on a test, I'll say, hey, you can use Desmos. Sometimes I'll be like, yeah, no, you can't. All right. This one's ugly enough that I'm going to say, yep, you can use Desmos. Now, what does that tell you? Well, you know 1 is a 0, and you know 3 is. And also notice, you know 3 is going to go into it twice because it touches or it bounces. So it has to be even power, like a parabola or a quadratic. So you know 3 is going to go into it twice, and you know 1 is going to go into it. All right, so let's go back. Let me get out of there. All right, so that's going to help me, right? So we said what? 3 twice and also the other one. Okay, so I'm going to do synthetic division. So this is what? 1, -7. I don't think we need any zeros, do we? We're not missing anything. That's why it's so long. All right, okay. Always bring down the first thing. And it seems like we've had a lot of 1s. They won't always be 1s. All right, I said that 3 is going to have what? Multiplicity of 2. So I'm going to divide, I'm going to use 3 as my 0. And I know my remainder is going to be 0 for sure because it touched. Multiply, add, multiply, add, multiply, what is that? -16, multiply, what? -48, and positive 36 and 0. Okay, that makes me feel good. All right, because I knew it was going to happen. Now, what you want to do on this is you want to build off your remainder. You want to take what's left and keep dividing because you want to get it down. I don't know. That kind of might remind you of like, Oh, I'm trying to think of an example where you just kind of want to keep dividing. Maybe like with trees, remember like when you do 36 and you go 6 and 6 and then you keep dividing like, oh, I want to build off of what I already do. Like prime factorization, maybe same idea. You want to build off of where you ended. All right, which means I am going to come off this. This tells me for sure it crosses at 3 because the remainder is 0. That means it's a root, an answer, a solution. All right, but we know it touched there. So we're going to do 3 again. So again, I'm going to bring down the 1. Always your first step in synthetic division. So multiply, bring down, money, debt, I owe debt, multiply, money, debt, I'd have $4 left, 12, -4, -12, 0. And again, I am not shocked because remember, I'm like, oh, this thing had multiplicity 2, it touched. Okay, now the thing that had, I think, multiplicity of 1, because obviously 5, it can't probably, be 3 or 5 or an odd, but it went through 1. Okay, so I am going to do synthetic division with 1 now. But again, on my leftover, because I'm trying to like factor this thing down in a weird way so I can either do quadratic formula or something. So bring your 1 down. 1 times 1 is 1. Now, be careful. 1 times 0 is 0. That can be easy to mess up. And then 4 and 0. Okay, so see, I am not shocked because I looked at the graph. I know that's all the case. Okay, now what is left? Well, we started with x to the 5th, right? So this is x to the 5th, x to the 4th, right? Or sorry, x to the 5th is here. Where's my new one? Right here, correct? Yeah. So this is x to the 4th, and then this is x cubed. So this should be what? X squared, okay? All right, so I went from x to the 5th, x to the 4th, x cubed. So this should be x squared plus 4. All right, so let's factor. Remember, factors are opposite of what they are. I have 2 of these, so I'm going to write squared, okay, because the zeros are at a positive 3, but the factor's here. Here it's at 1. And then I have what? X squared plus 4 left. Okay, so that's the factored form. And again, this gives me some information that I can graph, right? But we looked at the graph already. But again, I know I have odd behavior, not reflected. I know it's going to touch there. I know it's going through. Now, this is going to give you imaginary numbers, okay? So if they ask for all reals, so if they're like, okay, what are all the solutions, including complex ones or imaginary? There are 5 answers. There are 5. They're just not all real, okay? So here we have 3 is an answer with multiplicity 2, 1 is an answer. Okay, what about this? Well, this is where we need to know either quadratic formula and get imaginaries or whatever. I'm going to solve this. I'm going to set it equals 0, okay? Do, again, isolate an inverse. Square root both sides. Now be careful. When I square root, I get 2 answers. I get a positive and negative 2i. So those are my solutions or roots. I have 3 with multiplicity of 2. I have a positive 1 with multiplicity 1. And then I have these 2 imaginary numbers, 2i and a negative 2i. And notice they come in what we call conjugate pairs. They come in opposites. So if you have 4i, you're going to have a negative 4i. If for some reason you get an answer of 7 plus I, the conjugate would be exactly the same, but with that in the middle, negative. Or if you get a negative 17 plus I, you would have a negative 17, only the middle changes, minus I. Those are called conjugates, okay? All right, so we will do another example with those, and hopefully we can end with the videos on this section for you.